Hello, my name is Ravi Rao. I am a professor in the Department of Physics and Astronomy at LSU in Baton Rouge. And on behalf of the department and the EBR Parish Library, I would like to welcome all of you to this presentation of one of our Saturday Science at LSU. This is a series that began about 30 years ago in the early 90s and has been hosted by our department, and one scientist or engineer one Saturday a month during the academic year makes a presentation or a talk. And this was aimed at area high schools, the juniors and seniors who are interested in science. While the talks were always open to the public, our primary target were the high schools. Now, we do not give any credit or anything for these talks. It's entirely voluntary participation, and the students would come on their own. And the series has run very successfully with a good attendance for nearly 30 years. Some problems were developing with logistics of football Saturday conflicts and other things at LSU. And a few years ago, the EBR library very graciously allowed us to use their nice auditorium and host this event as well, co-host this. And we are very thankful for that. Now, of course, with COVID, we have been under suspension, and I'm hoping that everything will revive by the fall and that things will go well with the vaccines and so on that front for the nation. But this was a unique opportunity today with the Mars mission, which many of you will know about, which is currently sitting on Mars. And it was a unique opportunity also because one of our own alumnus, Keith Comeaux, has a very big role in this mission. And I'll introduce him in a minute. But before doing so, I would like to thank very much people at the EBR Parish Library, in particular Darcy Romer, Brandy Burton, and Julia Rigsby for putting this together, because I know that with this electronic thing, there has clearly been a lot of effort behind the scenes. But this is such a nice opportunity for us all, and I thank them. I also thank the graduate students who actually run this program, our Board of Regents Fellows, over the years, successive generations of them. And most recently, I want to mention in particular, Emily Saffron, Alexander Eagle, and our contemporary students who are indeed running the program, including the one for today. And with that, let me just say a few words about our speaker today, who is Keith Comeaux, the Deputy Chief Engineer for the Mars 2020 Perseverance Rover mission, which he will talk about. Keith was at LSU from 85 to 89, getting degrees both in mechanical engineering and in physics, after which he got an MS in aeronautics engineering at Stanford University. He also got an executive MBA degree from UCLA and has worked in the aerospace industry for a long time, first in NASA Ames and at the Hughes as a senior project engineer, and then in Boeing, and for many years now, including on the earlier Mars Curiosity mission for NASA and the Jet Propulsion Laboratory in California. And since 2017, he has been the Deputy Chief Engineer for this Mars mission, which landed a few months ago, and you will now hear about. So we are very grateful to Keith Comeaux, because this is obviously a very busy time for him. The mission is ongoing, that he agreed to do this for LSU and for EBR, sort of his native home. And we appreciate very much his participation today. So with that, let me hand this over to Keith Comeaux.
Well, thanks, Ravi, for that introduction. I'm really happy to be with y'all. Of course, Baton Rouge is where I grew up. It's my native home, and my family is still there, and I look forward to getting back all the time. Unfortunately, with the pandemic, this is kind of what we have to resort to, but it's very exciting to actually be able to share this mission and our success with all of you back home. So with that, let me jump in. I'm going to first share a video. Perhaps you've seen the video. Basically, it shares the highlights of our landing on February 18th, just a couple of months ago. So let me go there. And here we go.
We are starting the straighten up and fly right maneuver in preparation for parachute deploy. The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration. Skycrane maneuver has started. About 20 meters off the surface.
We're getting signals from MRO.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
Looks like we're getting the first image.
This is the most amazing thing. This is what NASA does. This is what we can do as a country.
All right, that is, oops, stop that.
We are starting the straighten up and fly right maneuver.
So those moments are always very exciting, and this one was no different. And frankly, was all the more special because we achieved what we did in the midst of a pandemic, which I think most of us are still kind of taken aback by, that we were able to do so much with the pandemic going on. We had just shipped our hardware to Florida for launch when the pandemic hit, and so we had to finish all of our testing and integration at Kennedy Space Center and launch and fly the mission through cruise and entry, descent, landing, and now surface operations still with all the constraints of a pandemic. So it's really been a challenge, but the team's been up for it, and it's really exciting to see the success that we've been able to achieve so far. So I'm going to share. By the way, I want to make sure my sound is coming through. Can I just can somebody just give me a
loud and clear?
Okay, good. Just wanted to make sure that I wasn't talking to myself. So I'm going to go through a presentation, which is going to be a very high-level overview of the mission. And I'm sure you will have questions. I'll take your questions when I'm done at the end of the talk. But I'm sure some of these slides might give you something to ask about. So yes, we launched on July 30th of last year, and flew Perseverance for 6.5 months, and landed on February 18th. And so now we're executing our surface operations. Just a little history about Mars exploration. Of course, we've been doing this for some time now. And ever since the early 2000s, there's been this mantra of follow the water. And we have basically built our orbiters and our rovers and landers to do just that, to explore Mars with the interest of finding possible evidence of habitability on the surface of Mars. We know today that there was once liquid water prevalent on the surface of Mars, like 3 billion years ago, just by looking at the surface features of the planet. But now we are also expanding that exploration into the particular geology, the types of rocks that might be good at preserving microorganisms from all those years ago, if they existed. And so that's kind of been the evolution of the Mars program over the years. And Perseverance is just the latest. And I'm going to talk a little bit more about Perseverance objectives. We've got 4 main objectives. Of course, the first is to study the geology of our landing site, Jezero Crater. with a particular interest of understanding whether or not it could have been a habitable environment for microorganisms 3.5 billion years ago when the crater was full of water. We're also looking for evidence of past life in Jezero crater. There is a fair chance that if life existed at that time, some of the rocks that we've been able to study from orbit may have been able to preserve fossil evidence of those microorganisms. And so we've got tools that will be able to examine the rocks for such microstructures in the rock, as well as the chemical composition. And I'll talk a little bit more about that. And really the main objective for Perseverance is really the first step of sample return, bringing rocks back to Earth for scientists to be able to study with all the tools and equipment that we have here on Earth. We can do a much better job of dissecting a rock and understanding what's in it and what its history might have been. In fact, you know, the moon rocks from the Apollo era 40, 50 years ago are still being studied to this day. As instruments become better and better over time, we can go back and study those rocks. And so that'll be a real key for understanding Mars in the future. And then lastly, we are preparing for human exploration of Mars. We have a few experiments on board, which will help us understand better how to live and work on the surface of the planet. You may have heard of an instrument called MOXIE, which is designed to produce oxygen from the carbon dioxide atmosphere. We also have a weather station, of course, to understand the weather patterns on Mars, as well as a radiation detector that measures the surface radiation from the sun and for potential exposure for humans on Mars. So these are the four main objectives. Again, sample caching is really the biggest reason for Perseverance, and it's going to kick off the multi-mission objective of bringing rocks back home to Earth. So here's the timeline of the Mars 2020 mission. Looking back, we selected our landing site way back in November of 2018. Jezero crater, you see it there. These were the three sites shown here: Columbia Hills, Syrtis Major, and Jezero crater were the three candidate landing sites. And we chose Jezero crater. Jezero crater is very interesting, and you'll see why in a minute. It was actually on the list of candidate landing sites for Curiosity way back in the late 2000s. But it wasn't selected because it was simply too hard to land Curiosity there. But we improved the landing capabilities of Perseverance. And so today we obviously were able to actually put Perseverance down in that very hazardous place. In the ensuing years, we designed and built the rover, and we launched it in July of 2020. We finished our cruise, landed on February 18th, and now we're in surface operations. So for most folks, Perseverance looks almost identical, like a twin rover from Curiosity, but there are some very distinct differences, and today you'll be able to spot the difference between Curiosity and Perseverance. I'm going to give you a few clues, but the clearest cue that you can actually see in this picture is the wheels. The wheels are actually very different, and if I go to, actually I'll come back to that in a minute, but you can see that we've redesigned the wheel. On Curiosity, the wheels experienced some punctures and some cracks that developed due to the nature of the surface that we didn't expect. The ground in Gale crater had these wind sculpted rocks, which were very pointy and embedded into the bedrock. And instead of, you know, a loose rock that you might drive over, just kind of rolls over as you're driving with it, these little sharp objects, which were embedded into the bedrock, actually created a very high concentration and poked right through the thin aluminum wheels. And then those poke holes actually developed into larger cracks over time. And if you've seen some pictures from Curiosity, some of those wheels look like they're in pretty bad shape. Good news is that they work just fine. But on Perseverance, we took those lessons learned and we redesigned those wheels. And you can see them on the right side of this image here. They're a little bit narrower, a little bit wider, a little bit thicker. And the most obvious thing is that you can see the treads have this nice little gentle wave in them, and there are many more of them. And so that's the easiest way to tell the difference between Perseverance and Curiosity. And cursor. So there's a few other differences, and let me start from left to right. The top left, you see the aft crossbeam. Perseverance is really a massive rover, substantially heavier than Curiosity was, and so we had to beef up its structure, and we had to put this roll bar that we call on the back of the rover to give it more strength. I already talked about the wheels. I mentioned the sample caching system that we have, which is really the centerpiece of this mission. That system is actually inside the belly of the rover, but what you can see in this image is a docking ring. In the center of the picture, and that's where the robotic arm inserts any rock samples that it gathers. It will deposit it into that sample caching system for processing inside. I'll talk a little bit more about that in a moment. Also, the turret at the end of the robotic arm is substantially larger than that of Curiosity. We have two instruments on the end of that turret, Pixel and Sherlock. They're designed to study rock structures very close up, including spectroscopy. And there is also a coring drill on the end of the turret, which we use to actually drill into rocks and pull samples out of the rocks to put in our sample caching system. And then finally, we have 23 cameras, very advanced cameras compared to Curiosity 17 cameras, some of which were in black and white. And you'll see some images from those cameras, and they're truly amazing and quite iconic in some cases. So here's another picture of how the wheels look different. These sharp angled treads on Curiosity's wheel really were sources for stress concentrations, and so we eliminated that in preference for this nice little gentle curved treads on Perseverance. And next. So this image shows a number of the cameras on Perseverance. As I mentioned, we have 23. All the way on the right side, Pixel and Sherlock both have imaging cameras for taking very close-up pictures of the rock to understand the microstructure of the rock surface. We also have a number of what we call hazard cams, both in the front of the rover and in the rear of the rover. They're similar to the function of Curiosity. However, we've much improved them, and they can produce very high resolution color images. And they really are the workhorse of the vehicle for navigating and sampling. And up on the mast, we have several more cameras. The Nav cameras, the navigation cameras, help us see the world on Mars in stereo, so we can see 3D and use those 3D images to smartly drive around obstacles on the surface of Mars. And then Mastcam Z is the workhorse science instrument that we use for taking pictures at various wavelengths of the landscape around us for scientists to better understand what we're looking at. And then lastly, at the very top, we've got SuperCam with a micro imager. SuperCam includes a laser that we can shoot at rocks. And when that laser hits the rock and vaporizes a tiny bit of that rock, it creates a little bit of a flash of light. And we can take a spectrum of that light and determine what the rocks were made of. And the micro imager also gives us basically, it's like a telescope. We're able to actually see very close-up details of a rock from far away. So next slide. kind of highlights the two instruments that are on the end of the robotic arm, Pixel and Sherlock. And we're able to look at a rock in great detail, and not only in visual detail, but also in chemical detail. We can actually, with Pixel, be able to map out, Pixel and Sherlock, be able to map out the chemical composition as a function of position on a rock surface. And between looking at the structures and understanding the chemical composition, we can make a very good educated guess on what we're looking at is whether or not it's a organic fossil from some past life, or if it's just some sort of a geological process that has created the structures inside of the rock. And those two instruments in particular are going to be very key in educating us about what samples we decide to actually cache in our system and prepare for a future mission to bring back home to Earth. And next slide. The sample caching system, as I already mentioned, is in the belly of the rover. So what the system will do when we've decided to extract a sample from a rock, we'll place that turret against the rock so the coring drill can drill into the rock, pull that sample out, and then deposit that sample inside the caching system. And then the caching system has another robotic arm inside it. And it will take that sample and move it through various processing stations to take a picture of the rock sample that we can see in the end of the tube, as well as measure the dimension of the rock that we get, and then ultimately seal it and store it or otherwise drop it on the surface of Mars for a future mission to pick up. It's one of the most complex robotic devices that we've ever built. We've haven't quite gotten to the point in the mission where we're actually checking out the sample caching system to make sure everything is working. But as soon as we're finished with our helicopter campaign on the surface of Mars, that's the next step, is to commission all of those functions of the rover so we can go about the business of selecting and caching samples. Here's just an image of the sample caching system being placed in the rover. It's quite an elaborate and complex choreography to get everything in the rover put together. And of course, we've got to do it in a super clean room. One of the big challenges of our mission is to not bring evidence of life from Earth to Mars and then discover that we have Earth organisms on Mars, because that would, of course, ruin our chances of finding Mars organisms. So we are very careful in constructing Curiosity to make sure that everything is very clean so we don't discover ourselves on Mars. Yes, and I kind of talked about our sample caching objectives. We're going to collect anywhere from 20 to 40 samples over the course of Perseverance's mission. And let me go to the next slide. Yes, the helicopter is another tech demo that we are doing, kind of like the first tech demo of a rover on Mars was the Sojourner rover that we launched with Pathfinder in 1997. It landed in 1997 rather. And so that was the first rover. It was the size of a microwave oven. It was really kind of a shoestring budget built with commercial parts just to see if we can do something like that. And the helicopter is very similar to that. It's very small, lightweight. It's less than 2 kilograms. It's kind of like a CubeSat, if you're familiar with those. But one of the challenges of flying a helicopter in Mars is that the atmosphere is very thin. It's only 1% as thick as Earth's atmosphere at sea level. And as a consequence, the blades have to rotate at a very fast speed, and the whole system has to be very light in order to actually get off the ground. We do have one thing working in our favor, and that's the Mars gravity is less than Earth. It's only about 3/8 as much as Earth. So our weight is lighter on the surface of Mars. But we've demonstrated that we are in fact able to generate lift with those blades at those Mars pressures in our simulation chamber here on Earth. And we're very much looking forward to, literally in the next week, to conduct our first flight on Mars. And here's a picture of the helicopter being installed on the belly of the rover. You can see it's all tucked in very compactly on the belly. You're looking at the solar panel and of course the blades, the carbon fiber blades, which are very, very light, right behind it. We did do quite a bit of testing of our system before we launched it, and this is just a highlight of one of our tests. The chamber I mentioned, this is the same chamber that it's a vacuum chamber, but we use this chamber to simulate Martian atmospheric conditions so we can fly our helicopter in it. And in this case, we're simulating the space environment to test our complete vehicle for the cruise from Earth to Mars. And this is what the vehicle looks like for that portion of the mission. So we did launch on July 30th. We got a little bit of a late start because of a launch vehicle issue, but everything got underway. And 6 months later, we arrived in Mars after traveling 334 million miles. We dropped into the Martian atmosphere at about 13,000 miles per hour. And so you've heard about the 7 minutes of terror. And this is where it comes from. We have to decelerate this vehicle from 13,000 miles an hour to 0 miles an hour in just 7 minutes. And all the while, we're basically disassembling the system until all we have on the surface of Mars is just the rover. So it's a very complex operation, and that's why we call it the 7 minutes of terror. The Curiosity and Perseverance missions used basically a capsule to protect the rover from the heat of reentry, as well as, it experiences about 11 or 12 Gs of deceleration through the atmosphere. And we used the Apollo guidance algorithm from way back when, 50 years ago. Apollo used a guidance algorithm to steer the capsule through the atmosphere to hit a particular target. We use that exact same algorithm to fly Perseverance and Curiosity to the landing site on Mars. We did make one update from Curiosity to Perseverance, and that's the deployment of our parachute. On Curiosity, we deployed our parachute when we arrived at a particular speed that was safe for parachute deploy. And in the case of Perseverance, we deployed our parachute not at a speed, but rather when we were at a location that was right over our landing site. And so that really helped us kind of get closer to a pinpoint landing on Perseverance and be able to land in Jezero Crater. So as you can see here, the deceleration that happened with the capsule decelerated from about 13,000 miles an hour at the top of the atmosphere to about 900 miles an hour when we deployed the parachute. Now this image gives you an idea of how we've improved our landing site ellipses over time. This is what you can think of this as kind of the runway that you need to put the rover down. Way back in 25 years ago or so, when we landed Mars Pathfinder, we're looking at a 200 by 70 kilometer ellipse, which is a ginormous area. So we would have to pick areas where everywhere in that ellipse, or essentially everywhere, is a safe place to land, which kind of constrains you to land in very large, flat, open spaces. And of course, big, open, flat spaces are not as interesting to scientists as something like you see in this image, Jezero Crater. And over time, we improved our ability to shrink our landing ellipse. Phoenix and Insight was 130 by 27. Curiosity, or MSL, was 25 by 20 kilometers. We landed in Gale Crater. And then Mars 2020 was about 7 by 7, almost a circle, 7 by 7 kilometers. And so we could place that landing ellipse very close to where the interesting geology is, which is typically dangerous to land in. And then the next slide, I think, yes. So the other thing that we implemented on Perseverance was a terrain relative navigation. And what this does is it gives us the ability to avoid hazardous obstacles that are in our landing site. The way we do that, we bring a map with us of our landing site that's been coded with safe and hazardous places to land. And once we're arriving at our landing site, we're falling on our parachute, the heat shield's been released, our camera is taking pictures of our landing site. We use those pictures, compare them to the map that we brought with us, and then we can select a safe place to land as coded on that map. And this is exactly what happened on Perseverance, and it worked like a charm. And gave us the ability to land in a really, really challenging landing site that you see here. Now, this is just one small spot within the Jezero crater, and the feature that I want to bring your attention to in the upper left side, that is a river delta in Jezero crater. The rim is a little bit washed out now, but the rim is on the left side of this image. And you can clearly see channels that are dropping into the crater and depositing a nice, fanned delta in the crater, which is clear evidence that this crater was once filled with water, and river and water flowed into this crater. And there's another part of the crater where you can see actually where the water exited the crater as well. So there was definitely a lot of activity at this crater a few billion years ago. And so, of course, the interest for our scientists is studying that river delta, because who knows what has been deposited in those sediments and preserved for us to discover on our mission. However, landing in a place like this is very challenging. And so we have, with the terrain relative to navigation, the capability of targeting this spot, but then when we get there, we can actually choose a safe flat spot to land, and that's exactly what happened on our mission. What happens is once we pick that spot, the power descent vehicle, which is basically the rover with its jetpack on its back, separates from the parachute. It diverts and flies to that safe landing spot using its 8 rocket engines, and then decelerates and lowers the rover on the sky crane. And once it touches down, it cuts those cables that you see there, and then the descent stage flies away. Now, one of the things that we added to Perseverance was a set of cameras to record all of those events during entry, descent, and landing. I'm going to show you that video. Perhaps you've seen it already before, but this is one of the most exciting things that I've ever seen as part, working on a Mars mission. It's never been, no landing on Mars has ever been recorded in the way that we recorded our landing on Perseverance. And so this is really going to be a source that engineers will go back to again and again to understand what happens during landing and improve our landing systems. So our prime mission is about 1 Mars year, 2 Earth years, and we will be making our way towards the river delta, and then ultimately climbing up through the various elevations, and ultimately driving out of the crater up into the watershed, if you will, upstream of where that delta is, to continue our mission. So that concludes my presentation. I'm going to show you a video now that I referenced, the EDL camera video that captured our landing. But I do want to point out a couple of websites that I would recommend checking out. And some of the stuff that I'm going to show you now is going to be from those websites. So hang on 1 second. And I'm going to go back to here. And we'll go here. And everybody, my sound is still working okay?
Yes, indeed.
Okay. All right. So this video basically goes through all of the events of landing from the point of view of the entry, descent, and landing camera. So this is actual video from Mars. We didn't get it in real time. We had to downlink it, many days after landing. But this is not an animation.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
So there's a few moments here where we're descending.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface.
So the rover is just gently swaying on the parachute as it descends.
Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Our landing site is right below us right there.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
All right. So that was, again, some of the most exciting videos I've ever seen, and quite iconic. I think those will live with us for for many years to come, as the Apollo images have lived with us for so long. So this, I'm just going to walk through a couple of images from our website, which hopefully will whet your appetite and get you curious and to go there yourself. So this is basically a map of Jezero crater. I can zoom all the way out, and you can see where our landing site is and where we ultimately landed. We had hoped to land right here in this nice little flat spot. We called that our landing strip. But as we flew a little bit long, and the computer had a choice of landing over here, and it decided to basically fly over this dune field and land in this safe spot right here. And that's what the divert maneuver was. And so we've kind of been hanging out pretty close to where our landing site was. And we've been doing checkouts, driving around. Right now, we're parked right here in preparation for the helicopter flight campaign. And that's what you see here in this blue racetrack looking shape right there. That's where the helicopter is parked. And basically, we're going to be doing flights back and forth within this blue oval and observing it from a safe distance away, where Curiosity currently is. So anyway, this is a great tool to follow not Curiosity but Perseverance over time. And then we also have image gallery. Many of our latest images are shown here. These are the ones that have been specially prepared and released. You can see some GIFs here of some of the testing that we've done of the helicopter spinning the blades to make sure everything is working right. This is the deployment of the helicopter from underneath the Rover a couple of weeks ago. And most of our recent activity is related to the helicopter, but we also have, here's, for example, every now and then we will take a selfie. And this is the first selfie on Mars with a companion in the selfie. Ingenuity, the helicopter, managed to participate in this selfie. And by the way, the selfie is taken with the camera on the end of the arm, where we actually hold it out just like you would a selfie stick or something. The only difference is that we have to take about 50 images because the field of view of this camera is so small, and we have to stitch all those images together. And then the other thing that I will point out is, what's going on here? There. All of the raw images come straight down from Mars and go right to this website without any processing, without any censoring. All of the images come right down on this website. And so you too can follow along in real time and see the images that are coming down from Mars. This is the latest images, like within the last, I could probably figure out. This image was acquired today. And this was an image taken with our remote microprocessor on the SuperCam instrument by the scientists who are studying a particular rock. And here's a few of the landscape images that we're taking around our vicinity. And every day we take a picture of the helicopter to make sure it's still there. And as we gear up for the first flight. So this is where to find all of the latest and greatest information about Perseverance. So with that, I think I would like to open it up for questions.
All right. Yeah, thank you for the great talk, Dr. Comeaux. This first question is going to come from Facebook. I read somewhere that there's a piece of a Wright brothers plane on the helicopter. Is that true? How did you sterilize it to avoid contamination?
Yeah, that is true. I'm not familiar with that particular, what they had to do to prepare a piece of that Wright flyer to place in Ingenuity. I'm sure they hermetically sealed it in some fashion, rather than apply some sort of heating process to destroy any microbes on it, which could in fact destroy the fabric itself. So I'm guessing that they sealed it somehow, but I'm not sure how they did it. We use Kept-on tape a lot, so maybe they use Kept-on tape.
Okay. This next question is also from Facebook. It's actually several questions. Is every action taken by the rover a pre-programmed series of instructions that are autonomously performed? Can it be driven manually? Is that due to the complexity of the navigation, the delay to give instructions and get feedback?
Yeah, so boy, this question really hit the nail on the head with regard to the complexities of how we operate on Mars. The first thing to know is that it takes light time to travel between Earth and Mars. And that means that any signal that we send between Earth and Mars takes light speed to basically go from Earth to Mars, and then the results of that action come back from Mars to Earth. That delay can be anywhere from 3 to 20 minutes one-way light time, based on where the planets are in relation to one another. When Mars and Earth are close by, when you can see it high in the sky, it's about a 3-minute delay, 6 minutes round trip. And if it's on the other side of the sun, then you're talking about a 20-minute delay, and round trip even longer. So we can't joystick anything with the rover. We do have to prepare instructions for the rover that it will then execute on its own. And the way we do that for surface operations, the rover wakes up every morning at about 9:20 a.m. local Mars time, and basically turns on its radio receiver, points the antenna to Earth, and listens for instructions. And that's when we send up our instructions from the Deep Space Network. And once the rover gets its instructions, it says, "I've got my instructions," by sending a beep. And then it goes about its business of executing the day's activities, both, taking pictures, doing housekeeping, science activities, driving, hardware checkouts that we're still doing. And then later in the afternoon, we start having overflights of some of the Mars orbiters that are there. Each one of those orbiters has a relay radio, and Perseverance will turn on its UHF radio and transmit the results of all those activities to the relay. And then that relay will then forward those results to the Deep Space Network, and then that's when we receive them. So it's all very asynchronous and autonomous. We do put a lot of smarts in the rover. So we have something called auto nav. As we start doing more driving, we'll be able to basically give it very high level instructions to drive to a certain landmark. And then the rover itself, using its cameras and using its computer, will be able to determine on its own how to avoid the obstacles that are presented to it and arrive at that destination. And so we're, every mission we get better and better at expanding the autonomous capabilities that we give to the rover. And that helps us get more done in a faster amount of time. So I think I hit all the points of that question, but if I missed one, let me know.
Okay. Emily says, "Hello, Dr. Comeaux. Thank you so much for your talk. Were real-time landing decisions a mix of commands from the JPL crew and AI already on Perseverance? Communication delay pose any challenges?"
Yeah, same story, actually. We had to rely on the autopilot during landing. So what we did is we gave Perseverance everything it needed to know about 5 or 6 days before the landing actually happened. We loaded its memory with the best information that we had about where it was, what its speed was, what time it was going to arrive at Mars. In addition to, we had to take into consideration what the atmospheric conditions were at Mars. And so our controller could appropriately respond to it. But again, all those instructions were developed, prepared, and sent to the rover several days ahead of time. And as we got closer to Mars, our knowledge of where Perseverance was in relation to Mars improved. And so we would give it some knowledge updates once in a while as we got closer to Mars. But other than that, it was really on its own. And so we used the autopilot, which had been thoroughly tested both on the flight hardware during integration and test, as well as in computer simulations. We ran millions of computer simulations, and we varied a lot of the inputs and to those computer simulations to ensure that the autopilot would work in a variety of circumstances that it might experience during the actual landing. And so, yeah, we were well prepared for it, but at the end of the day, it's got to do it on its own.
Okay. I apologize if I mispronounced this name, but this question comes from Gurminder Kaur. Will the Perseverance rover help in finding what sorts of geological evolution Mars went through?
Yes, and now, so I'm gonna get out of my expertise a little bit, but one of the interesting things about this crater is understanding, the timescales of how this crater formed and how the different eras of, wet and dry periods may have, the crater may have experienced. And so one of the things that we're going to be doing is looking to bring samples back that will help us date the various geological units that are inside that crater. And so that will help paint a picture of the various, phases that the crater had experienced over time. It's possible that, there could have been a very wet period, and then it could have dried up, and then more wetness in a different year. I think those are the kind of questions that we'll try to answer, as well as, of course, looking for evidence of preserved past life in those rocks.
This next question is from Ned Denby. Is there anything you're hoping not to find, meaning anything that would jeopardize future missions and or human habitation?
Oh, that's an interesting question. I think the biggest thing that we're hoping not to find is evidence that our sample caching system is contaminated with Earth organisms. That would be the worst, because that would pollute our science results. There's a saying in science about, extraordinary claims require extraordinary evidence, and declaring that we've found evidence of past life on Mars is one of those extraordinary claims. And if we had brought Earth microbes with us to Mars, that would really pollute the claim that we found something on Mars. So I think that's probably the worst thing that we would hope not to find.
This next question is from Facebook. Is there a new date for the Ingenuity to take flight?
Boy, getting right into the real-time operations here. So I just came off of a 3-day stint, and it was still very uncertain when Ingenuity was going to fly. It's going to be in the next week. I'm pretty confident that that's the case. However, we're still working through a flight software glitch. We've got 2 workarounds that we're still pursuing. One is a flight software patch to help the flight controller boot up into flight mode, and the other is just a wholesale flight software update. The flight software patch, of course, is an easier implementation, but there's some idiosyncrasies with it that we're still working through. But the flight software update is something that we're also prepared to do, but will take longer to get to that first flight if we have to go that route. And so I'm out of the loop for about the last 36 hours, but that's kind of the path, the 2 paths that we're on right now.
This question comes from Kai. How exactly did you know where to land?
So let's see, there's 2 ways to answer that question. The landing site selection was, a very well-organized and disciplined process that helped the scientists basically enumerate all of the objectives of a place that we wanted to study. And the various landing sites had to be somewhere where we had a high confidence that if there was past evidence of life, then that we could potentially find it in those locations. And so that really guided the landing site selection itself. Now, part 2 to that question is once we're actually flying, and about to land, there's many obstacles within that landing site, and terrain relative navigation is really what made that final choice of what spot to land on within the landing site. And it made those choices based on a map that we sent with the rover, that humans basically poured over all of the images that we got from the orbiters over Mars, and basically mapped out all of the obstacles in the landing site. And so we basically told Perseverance, do not land in these spots because you may not survive. And so with that information, it chose the final landing spot based on where it was at the time that it separated from the parachute.
This next question is from Francis Din. As a studying architecture student, one of the things I'm most fascinated by is the design of the rover and helicopter. Are there press releases or anything available online that we can access that goes into how these robots were designed? I'm hoping to one day design the first architectural structure in space.
Wow, fascinating question. I would have to do a little research to point to something that might be useful, but what I can tell you is that we did a bunch of YouTube videos when we were constructing both Curiosity and Perseverance, which kind of narrated all of the testing and design efforts that we did along the way. And so I would recommend, I think it might be the JPL YouTube site, which might have some of those videos. Other than that, the other thing I would recommend is just looking in scientific conferences and papers, journal articles, searching for Curiosity and Perseverance. A lot of things do get published by our team in how we design things.
This next question is from Gurminder Kaur. What is your favorite question which lies beyond the scope of this mission?
I don't know if I have a favorite, but I'll tell you, the one question that I always get is about humans to Mars. And that's a really hard question because, that's kind of been something that folks have talked about and dreamed about. And it's always seemed to be about 2 decades out into the future, ever since we landed on the moon. So it's a very hard thing to predict, when and whether we'll ever, make it a national priority to send humans to Mars, because it will be a very expensive and a very dangerous trip to make. I personally, my own personal feelings is that the moon is right in our backyard, and there's a lot we can do on the moon to develop all the technologies and procedures and understand how humans behave in space over a long period of time, just right here on the moon in our own backyard before we actually commit to something like Mars. So yeah, we at JPL are mostly involved in the robotic exploration of space, and it's a lot simpler than trying to include humans, which you have to provide life support systems as well as a way to bring them back home. And so robotic systems are a little bit easier than sending humans out there to do exploration.
Okay, this next question is actually from me. So you talked about being able to divert the capsule as it's landing. How far is it actually possible to divert it approximately?
Yeah, good question. We actually were having discussions about that late in cruise because there was an issue that we discovered. And it's on the order of about 700 or 800 meters is about the limit of how far we can divert once we let go of the parachute. And so beyond that, you start, your control authority starts to get maxed out, and you may not make it.
Cool, thank you. Are there any more questions? There don't seem to be any more in the chat.
Yeah, go Bears. I see that in the chat.
Well, if not, I think I would like to thank Keith Comeaux for a fascinating talk and all the nice videos. And I know he's multitasking and we have to let him go. But Parampreet Singh, my colleague, and I, who run this program for the Department of Physics and Astronomy, would like to thank all the library personnel, our graduate students, and most of all, Keith Comeaux for doing the Saturday Science presentation. The first for us on Zoom, but it all seemed to work very well. Thanks to all. Thank you very much.
Thank you.